Hello everyone, this is BSc third year class of complex analysis. So yesterday we have discussed what is mean by complex number. So complex number is a Z, it is generally denoted by the letter Z and it is written as x comma y. The meaning of x comma y is x plus iy. So this is the real part of the complex number and this is the imaginary part of the complex number. Now if we can say that every real number is a complex number. If y is equal to 0, then z becomes x. Then we can say that every real number is a complex number. But every complex number need not to be a real. Also we can say that if x is equal to 0, then z is equal to iy. Then we say that this number is a purely imaginary number. If the real part of the complex number is 0, then we say that the number is purely imaginary. Now today we are going to discuss what are the basic algebraic properties of the complex number. Basic algebraic properties of the complex number. Of the complex numbers. So what are the basic properties of the algebraic what are the basic algebraic properties of the complex number? We know that set of complex numbers is a field. So it must satisfy 11 properties of a field, but it is not an ordered field because it does not satisfy the ordered structure at 4 properties. So we can consider first property. So commutative property. Commutative property. If Z1 comma Z2 belongs to the set of complex numbers, then we know that Z1 plus Z2 is equal to Z2 plus Z1. If Z1 is equal to x1 comma y1 and Z2 is equal to x2 comma y2, which is equal to x1 plus x2 y1 plus y2. So we can interchange the role of x1 and x2 plus x1 comma y2 plus y1. So what it is? x2 y2 plus x1 y1, which is equal to z2 plus z1. So addition of the two complex numbers is associative. Now multiplication, z1 into z2 is equal to x1 y1 into x2 y2. So it is what? x1 x2 minus y1 y2 comma. We discussed how two complex numbers are multiplied yesterday. x1 y2 plus y1 x2. So this is the multiplication of two complex numbers. Now consider z2 into z1 is equal to x1 y1 x2 y2. Then it is x2 y2 x1 y1. Then it is x2 x1 minus y2 y1 comma x2 y1 plus y2 x1. So we can write this as x1 x2 minus y1 y2 because these are the real numbers and we know that the real field is a commutative. y1 x1 y2 plus x2 y1. So compare 1 and 2, then we can directly say that z1 into z2 is equal to z2 into z1. So this is the commutativity of multiplication. Now associativity. associative property. Second, associative property. Associative property. So consider three complex numbers Z1, Z2, Z3 belong to the set of complex numbers. Then Z1 plus Z2 plus Z3 is equal to Z1 plus Z2 plus Z3. So we can verify this. So Z1 is x1 y1. So this sum is x1 plus x2 y1 plus y2 plus z3 is x3 y3. So it becomes x1 plus x2 plus x3 y1 plus y2 plus y3. Now consider now if we consider Z1 plus Z2 plus Z3 is equal to x1 y1 plus, so this is x2 plus y2 and x2 plus y2 x2 plus y3 sorry x2 plus x3 x2 plus x3 and y2 plus y3. So this becomes x1 plus x2 plus x3 comma y1 plus y2 plus y3. So we can compare 1 and 2. So from this we can directly write z1 plus z2 plus z3 is equal to z1 plus Z2 plus Z3. So addition of three complex numbers is associative. So this property is verified. Now you can check for the multiplication. Check for the multiplication. That is, we have to check that Z1 times Z2, Z3 is equal to Z1, Z2 times Z3. So it is obviously equal because this is a field. So you can verify your own. So we leave it for a homework. Now third, now third, distributive property. Distributive property. So in this, Z times Z1 plus Z2 is equal to Z1 Z2 Z1 plus ZZ2. So you can also verify this. So consider LHS, it is XY. So this addition is x1 plus x2 y1 plus y2. So multiplication of these two x times x1 plus x2 y times y1 plus y2 minus into x times this, x times y1 plus y2 plus y times x1 plus x2. This is, and multiply these two, then you will get these two multiplications are same. So we can directly say that the multiplication of is distributive over complex addition. Now fourth property, additive identity. For any Z belongs to C, there exists 0 belongs to C such that Z plus 0 is equal to Z. That is, if Z is equal to x plus y, then 0 plus 0 is equal to x plus 0, y plus 0 is equal to x comma y. So for every z belongs to C, there exists a number 0 in C such that if we add this number to any number, then there is no change in the original number. So this is the additive identity of the complex number. Now additive inverse. We know that now additive inverse. Additive inverse. If z belongs to C, if z is equal to x comma y belongs to C, then we can say that minus z minus x comma minus y also belongs to C, such that their addition z plus minus z is equal to 0. Therefore, minus z is the additive inverse of z. So additive inverse of each and every element of the complex number exists. Now multiplicative identity. Multiplicative identity. If now multiplicative identity of a complex number is 1. Multiplicative identity of a complex number is 1. So 1 can be written as 1 comma 0. It can be written as 1 times 1 plus I comma 0. So multiplicative identity of complex numbers is 1, and it belongs to the C because 1 comma 0 can be written in this form. So multiplicative identity of the complex number exists and it belongs to C. Now multiplicative inverse. Multiplicative inverse. So if z belongs to C, then there exists z dash belongs to C such that z into z dash is equal to its multiplicative identity. We have to find the value of z dash. So if let z is equal to x plus iy is equal to x comma y. So z dash is equal to 1 by z is equal to 1 plus x plus iy. So rationalize this x minus iy divided by x plus iy into x minus iy. So multiply both numerator and denominator by x minus iy. So from this x minus iy. So this is a plus b, a minus b. So we can write it is a square minus b square. So x square minus iy square. So it is x minus iy divided by x square plus y square, because I square is equal to minus 1. So multiplicative inverse of a complex number z is multiplicative inverse. So z dash is what? X minus iy divided by x square plus y square. It can be written as x divided by x square plus y square comma minus y divided by x square plus y square. So this is the multiplicative inverse of the complex number z. Now some examples. Example first. Prove that first. So first is root 2 minus I. Root 2 minus I minus I times 1 minus root 2I. 1 minus root into I is equal to minus 2I. That we have to prove. So consider LHS. LHS is equal to n square root minus I times 1 minus root 2I. So root 2 minus I. So multiply by I inside minus I square is minus 1 plus root 2. So this becomes root 2 minus I minus root 2. So root 2 cancel. This is minus 2I is equal to RHS. So this is the example first. Now consider second. 2 comma minus 3 minus 2 comma 1 is equal to minus 1 comma 8. Now you can write this number as 2 minus 3I into minus 2 plus I. So this is LHS. So multiply 2 into minus 2 minus 4. 2 into minus 2 minus 4. Now minus 3I into I is 3I. So 3, it is minus 3. So now multiply it directly. So 2 minus 4. So multiply 2 by I plus 2I. So multiply 3I by minus 2I. So it is 6I plus 6I. Now multiply minus 3I by 3. So it is 3. So it is 3. So calculate. So minus 4 plus 3 is minus 1. And 2I plus 6I plus 8I. So we can write it as a minus 1 comma 8. So this is our RHS. Now third example. 3 comma 1 minus 3 comma minus 1 into 3 complex numbers are given. 1 by 5 comma 1 by 10 is equal to 2 comma 1. So directly calculate multiplication of these two complex numbers. So 9 plus 1. Now 3 into minus 1 minus 3 and 1 into 3. So it is 3. So it is what? 1 by 5 into 1 by 10. So this is 10 comma 0 and it is 1 by 5 comma 1 by 10. So calculate this. 10 into 1 by 5 it is 2 and 0 into this is 0 comma 10 into 1 by 10 1 plus 0 into 1 by 5 it is 0. So it is what? 2 comma 1. So it is RHS. Now another example. Show that first real part of I times Z is equal to minus imaginary part of Z. Minus imaginary part of Z. So we have to show this real part of I times z is equal to minus of imaginary part of z. So consider Iz is what? I times x plus Iy. So multiply by I inside Ix minus y. So now the real part of this is, so Re of Iz is minus 1. Now consider imaginary part of z. Minus of imaginary part of z is minus of imaginary part of z is y. So it is equal to minus y. So from 1 and 2, real part of Iz is equal to minus of imaginary part of z. So now example second. Imaginary part of Iz is equal to real part of z. So now Iz is what? I times x plus Iy is equal to Ix minus y. So imaginary part of Iz is minus y. So real part of z is imaginary part of Iz is minus y, and real part of z is equal to real part of x plus Iy is equal to x. Sorry. Now the imaginary part of I times x plus Iy is equal to imaginary part of Ix minus y. So imaginary part of this is x. So imaginary part of Iz is x. Now real part of z is equal to real part of x plus Iy is equal to x. So from 1 and 2 we can say that imaginary part of Iz is equal to real part of z. So today's lecture I am going to stop over here. Tomorrow we are going to discuss some other properties of the complex number. So thank you.